guys! Hello everyone! Who have been my event before? Nice! Almost 1/3. And for the ones their first time being here, welcome to our meetup. And we're very active. We almost have 1 to 2 events per week. And we welcome you to become a speaker. I started meetup in May 2013. At that time, I was doing a lot of volunteering, like food for homeless, and I started to realize I need to teach people this skill. So I voluntarily teach Python R in my meetup, and for half a year later, I got my school. So volunteer will lead you to somewhere awesome. So if you have solid skill, if you have something to share, please talk to me. And we start to ask our students to present their work. Because they just go through the 12-week full-time program, they're ready to be a data scientist. If you have any opening in your firm and you like them, like their work, please talk to them. Everyone is looking for a job now. We have 20 awesome candidates. We typically train people in master and PhD level from science, engineering, math, statistics background. We cannot teach people math in 12 weeks, but we can teach you coding in 12 weeks. We were get started with Chris and Amy. Who would start? Okay, come in. You're hiding, so I'm not sure. So please introduce yourself, and if you're look for a job, tell them what kind of job you look for. Let's get started. Thank you guys.
Hi guys, I'm Aravind. I have a background in statistics, and I'm currently an analyst with Hillshade. Yeah, I'm looking for interesting work in machine learning.
Hi, I'm Thomas. I have a background in economics, and I'm also looking for something data science related.
I'll be more specific.
More
What do you mean
specific?
you have background?
I studied economics, so yeah.
Thomas have Bachelor of Economics from Harvard, and Aravind got Master of Statistics from Columbia. Oh, get started.
So so for our machine learning project, we looked at a famous data set famous, I guess, in the machine learning world, that involves forest cover type from this one forest in northern Colorado. And to show where it is, as you can see, there are a few different areas, and the data set covers 4 separate wilderness areas. And within those areas, you have 7 different tree cover types. You have spruce trees, lodgepole, ponderosa, cottonwood willow, aspen, Douglas fir, and crumhulls. So looking at so basically what we're supposed to, it was in a Kaggle format. So what we wanted to do, the purpose of the competition was to be able to predict forest cover type based on the features that were available. And this was an interesting problem because since it's an older data set, it's been used. You could see how in the past there have been improvements on prediction as new algorithms have been developed. And also in the specific Kaggle competition, the training set was much smaller than the testing set. There were only 15,000 training observations and 500,000 testing observations, so that made it an interesting challenge as well. So we used R for this project, and some of the variables that were in the data set were elevation, just how high on the mountain this specific 30 by 30 meter observation is, and the aspect, which is the direction that the slope is pointing downwards, the cardinal direction, like 360 degrees, so 0 degrees north or east or a different direction. And then the slope of each observation, the distance to water, and then distance to roadways, and then we had Hillshade at 9 a.m., noon, and 3 p.m., so that was a variable explaining the illumination at a point. And then also a few other factors, which I'll show in a moment. And the response variable was cover type. So looking at elevation, this was probably the feature that was easiest to see some pattern in the data set. So there's some trees that only exist at higher altitudes, like the Krumholtz, and but there is still a lot of overlap between them. So looking at the density plot, we can so that was a histogram. Now looking at the density plot, we can see there's overlap. So we can't classify forest cover type based on this alone. And with the 4 wilderness areas I showed you, there's some patterns, like you know that some forest cover types aren't present in every single each of the areas. So, and there were also 40 different categorical variables for the soil type, involving whether, like, how stony the soil is or some other materials in the soil. And while all of this separately tells you some things about the data. Next, so looking at aspect, since this is in the Rockies, it makes sense that more of the land has like a downward slope to the east. This is the Eastern Rockies, and the Great Plains are there. And although there's some differences you can see here, like with where certain cover types are like positioned, they were still only getting like an incremental understanding of the data.
I just wanted to add that so we don't have the position right up here, but if you look at this, it's kind of actually north. So we have more patches of land pointing in the easterly direction and westerly direction, and kind of indicating that, yeah, I think the Rockies run from north to south. So I think that's our inference that we got, that the aspect is usually easterly or westerly.
And we also seeing like the 4 wilderness areas, there also seems to be, they all seem to have, they all have observations that are pointing in the different aspect directions. Okay.
This is a little large, but yeah, this is right. So what we are looking at is kind of a correlation plot along with density plots, as well as like correlation values across classes for all the quantitative variables in the data set. What we are looking for is some kind of correlation, some kind of class separation. We're looking at interesting patterns, if at all they arise, and we want to understand why they arise in the data set. So some of the interesting, if you look at this chart between, I think it is Hillshade and aspect, and if you look at between Hillshade at Hillshade at two times of the day, we get something like a convex parabolic shape. So we wanted to elliptical shape. So we wanted to look at we want to understand why all these features are occurring, and can we see any class separation clearly in this particular chart. So you can see that there is these charts over here which have elevation, with comprise of elevation, usually you can kind of split the data into different colors, but you can kind of tells you that elevation may be like much more relevant as a variable than others. So we'll try to figure out why these shapes occur first. So Hillshade is it's a cartographic variable. First we were thinking, why are these variables collected? Why these cartographic variables are being conducted? It's usually for terrain mapping and apparently remote sensing applications that it is used for. And over here we see, so Hillshade is, can you go a little bit? So Hillshade is defined by this equation here. It's essentially saying that it's proportional to So the illumination or the light on the patch is proportional to where the sun is at some point. It's also proportional to this direction, the relative direction, the slope of the slope is pointing to, and and the direction where the sun is pointing to. So this is given by the cos of the azimuth minus aspect, which basically azimuth is just saying that the direction of where the sun is pointing to right now. So if I have a patch pointing directly at you, I would receive more illumination. And if there is a plane slope, I would get more illumination. If it's kind of tilted, I would get lesser. So this arises from a theorem in spherical geometry. It's kind of easy to prove if you use some vector algebra, but essentially it basically talks about vectors. Basically, if these are like 3 points in a spherical space, and these points joining together are basically the lines joining a great circle joining these points, and similarly for these two, you can actually derive and this is a unit sphere. This if you look at the center of the sphere corresponding to like if you look at the center of the sphere, the angle subtended by the sphere to these 2 points essentially is the angle in radians. That is this value, the value of uv is actually the value in radians of the angle subtended by the points u and v. So if you go down like so you can actually just prove this equation. So essentially the idea is that the patch illumination is related to the altitude of the sun, the slope, and the relative direction of the sun and slope at that point. So we just plotted a couple of plots to show you. One which does not really show us class separation, but it shows us the shape that of Hillshade at 3 different times. So this is just like a Hillshade plotted at 3 different times. If you go further down, we plotted 3 different variables that kind of be used to show some class separation. This is elevation, slope, and Hillshade. These are 3 different variables. It's a 3D plot. And what we are seeing is that when we could easily like slice this plot into like its constituent classes in some format based on like these variables, showing that some of these elevation and especially elevation, proving that it is a more significant indicator for this particular classification problem.
So next looking at our actual machine learning modeling of the data, so first we covered a lot of the data exploration that we had to do, and we also did a lot of feature engineering. But so first we used the features that were given in the Kaggle competition, and we ran multinomial logistic regressions on them to start, and then we tried neural networks and tree-based models, including random forest, gradient boosting, extreme gradient boosting, and extremely randomized trees. So we both did that with the original data and then with the features that we engineered. So looking at the features we engineered, we tried a few different combinations of we looked at like the mean of Hillshade from 9 a.m., noon, and 3 p.m. We took the Euclidean distance to hydrology, and we made we also summed a few different features together to see if they would show up better in the models. We also looked at, we classified aspect group into, to see whether it was large or small, to maybe see if that would pick up more easily than just looking at having each individual value of aspect. And we also tried a few more. We spent a lot of time trying different variables and like breaking apart different variables that were already there. So like the types of soil, we broke them apart into the family and rock type. And then we also did interactions where we multiplied 2 features together to make a 3rd feature. So the first model, we were looking at logistic regression. So so it's a multinomial logistic regression where we are predicting 7 different classes. So that means since a multinomial regression, logistic regression is sensitive to, has a higher variance, we had to make sure that we regularized it. So, okay, so this first equation up here, it shows how basically what we're doing is summing up the 7 different probabilities for the 7 different classes. And the left side of this equation, it's basically, here we take the negative likelihoods and we're adding them up for the 7 classes. And then n is the number of observations, so then we have to add that up for all the observations in our training set. So that's the left side of the equation. And then our regularization basically happens here on the right, where if alpha is 0, we have ridge regularization, and if it's 1, we have lasso. So, and basically the differences that come from that are with ridge, your features that aren't so important are basically made a lot smaller, a lot closer to 0, and then with lasso, they can actually be made 0. So looking at when we ran our ridge regularization, and we tuned it, we ended up getting around like upper 50, like 59% accuracy when we would like posting it on Kaggle. And what we chose, I'll raise this a bit. So basically the lambda term, or the term that determines the shrinkage of the features, that is what we spent the most time trying to find. So this plot shows, it's a plot of multinomial deviance, and essentially this is what, so we used the glmnet package in R, and with it we were able to find the value of lambda that basically gave the smallest multinomial deviance, which is essentially tells us which is like the best model, which is the model which is the closest to, which is the most accurate. So that was for our ridge regression. For our lasso, it was similar, but the results that we got were a slight improvement, but also about the same. There's not much change. So there's also an elastic net regularization for our multinomial logistic regression, and it's basically a hybrid of the two, where instead of choosing like lasso or ridge, it's somewhere in between, and it did about as well. Also, there wasn't much of a difference between those. So we went to, next we see whether we improved much with neural networks.
So we initially tried single layer, hidden layer feed-forward neural net using an NNet package. There were not many parameters to tune here. We tuned the number of nodes over here, and then we were able to we chose I think a model that had about 100 layers with which gave us only about 52% accuracy on this data set. So based on this, we also used the deep learning package H2O, and we had a lot more to tune in that regard. So essentially, they run they have this they use parallel distributed algorithms to improve the speed, and they also have a lot more parameters that you can train and use to build the model. So we try to vary some of the parameters in the H2O model, and in the end, what we realized was we had an improvement over the single layer network by about 15%, I think. So we improved it about 67% after some tuning. So, but what I wanted to talk about more was some of the earlier work done, which is kind of interesting. So, so the data set was initially, I think, was collected in the late 1990s, and I think at the Colorado State University, some couple of people used it for doctoral dissertation. They were able to get about 70% accuracy on an ANN model. And then a couple of people used a different kind of approach. Need not necessarily be a machine learning, but they used something called as rough set theory. It's like a variation of, it's like an approximation of a general set theory that we use, and they apply it on decision tree models. And they actually were able to reduce the variables despite having very high accuracy in the data set. So they got about 78% accuracy on that. Another interesting paper, which we should mention here, is in 2004, a couple of professors from the University of Notre Dame, they experimented on this data set, and they figured out that there are some there's this class of data sets which are definitely always better, it's always definitely almost always better to use tree-based methods rather than neural nets. And they synthesized these class of problems, and essentially what they see is that if you have a class overlap in your visual, like when you're looking at the visualization of the class, you see class overlap from one on top of the other, you kind of tend to go for some kind of a tree-based method rather than this traditional feed-forward backpropagation or any kind of neural network in this regard. So that is what is mentioned over here. So based on this, we kind of started to look at tree-based methods, and I think some of you may have familiar with some of the stuff, and some of them are newer algorithms which are just like variants of some of the others. Random forest is a basic. We know what random forest does. Essentially, it samples rows and columns to build the trees and ensembles different trees to get the result. I mean, even though it induces some bias, but the variance is greatly reduced because of the ensembling. The gradient boosting is dependent. It fits consecutive trees dependent on one on the other. Basically, trying to kind of minimize the error out of the net error of the previous trees. The XT boost and GBM are essentially gradient boosting methodologies created by different people, and essentially they offer higher, like faster implementations and greater parameter capabilities, and you can also use randomized hyperparameter search. So essentially you can build models where you can, instead of going through a brute force grid search method, you can look at, you can iterate over like 100 iterations, choosing randomly the different parameters that you want to kind of change on, and then optimize that. So, and then finally we use something called as the extremely randomized trees. These are, and they're also known as extra tree models. Essentially, they are random forests, but with some basic changes. So they use the complete sample, and they also randomly randomly like splits nodes. And the cut points that are chosen while you are building the tree are made entirely in random. So it's kind of weird that how something like this can actually work, but apparently, like, I mean, actually it did. So I just wanted to like show you each method and how we work. I don't know if we have time for everything, but we just run over almost everything that we did. So initially we did random forests, like even without any sort of tuning any parameters, we got a better result than the artificial neural network, and then we started tuning the neural network to get a better result. We also used the feature engineered variables versus the original data set that we had. So we compared both of them. We considered each variable. I mean, the variables considered each split was varied, and we kind of optimized to tune our model. And I think in the end, we got about 75% accuracy based on just random forests and if we look If you look at the feature engineered data set, we got a slightly worse result. We're not sure exactly what happened. I think we tried a bunch of different variables, and we also tried using including the features like one by one. We chose the most important variable in the model, and then kept adding the most important variable one by one, and then we ultimately we were able to get only about 72% accuracy when we used the feature engineered model. And then so we started exploring XGBoost. I think this was a model that a lot of people at Kaggle were using, and we wanted to see how it worked in our dataset. Um, we so as we mentioned before, it's essentially a gradient boosting model, and the multinomial log loss is a parameter that we use, which basically we choose to optimize. We wanted to kind of minimize the log loss for different at some point where it does not overfit. So the feature, so we tuned the parameter and we achieved about 73.4% accuracy on this, and then we looked at the most important features in the XGBoost, and then we started sequentially adding variables based on their importance. So this particular graph shows you if you increase the number of variables you add in the model, what is the accuracy level that you obtained cross validation, and also the number of rounds for the same where the log loss is minimized. As you can see that it does not really depend on the number of variables added. So almost I think stabilizes around 100 rounds, and we ended up getting an accuracy of about 72.66, still lower than the one achieved using the original dataset. It looks like the dataset it's requiring a lot of variables to achieve the best optimal sort of accuracy levels. It requires a lot more than just using, or dimension reduction is not essentially helping out. So and we tried gradient boosting models using H2O, and yeah, that was kind of an improvement. So I think what happened was, I think that the gradient boosting, the packages that are available in I think in R, we use R actually for the whole thing. So I think I forgot to mention that. And what we realized was that uh, the the gradient boosting H2O model does a lot better than the vanilla gradient boosting model that's available out there in R. So I think it's actually a good practice to probably use this from now on. Essentially, you can do a lot more tuning, and it's much faster. And the tuning of these parameters ended up in one of I think the some of the best model from gradient boosting gave about 78% accuracy. So, and then finally we wanted to look at the extremely randomized trees. So as we mentioned earlier, it's essentially random forest, but with certain two important changes. It's just that it uses the whole of the in-sample data each time to build the tree. It does not cut the tree into into different smaller samples. At the same time, it chooses the cut points of sampling at random rather than the traditional way of tree building. So this accuracy, so there were 4 different parameters to tune in this particular model. So we went about in a sequential manner. We first changed the accuracy. We first tried to get the number of trees optimized first, and then number of variables optimized after that. And then we simultaneously varied 2 different parameters and kind of chose the optimal sort of mix that we want for a final model. And we got an accuracy rate of about 79.25%. I think that was the best result that we had.
Yeah.
And,
So then when we tried to ensemble some of these together, it didn't really end up helping, so that was our best result. So we tried a few different methods. For those who don't know, ensembling is basically just you could use different ways to put the best results from our different models together to see if they make a better result. So the simplest way to do that is just by voting. So for each observation, we saw like what each model, which each of our best models, like what it predicted as a class for the observation. But when we summed them together, it didn't do as well. Then we also did some slightly more advanced ensembling, where we did things like feed extra trees, like the results from extra trees into the GBM model. But none of that in the end did as well as just the extremely randomized trees. So and we ended up getting in the top 13% of the Kaggle ranking. Although it was more just it wasn't a competition for money, because the data set was already public, so somebody even got like a perfect, like a 1.0 on it, because somebody, I mean, maybe that's the best data scientist there is, or the person who used the data set. We also, we saw some people did slightly better than us, and it was most likely due to slightly better feature engineering. And we found that feature engineering really took a long time. We spent a lot of time looking at that the large plot with all the with the 11 different variables. So we spent a lot of time trying to figure out different variables and see if there was anything. Basically, when you're feature engineering, you want to see if there are variables that aren't being picked up by the machine learning algorithms you're using. So, I mean, some of the more obvious things are picked up by tree-based algorithms and neural networks, but so we tried a few methods, and it didn't work out as well as we hoped. But overall, it was an interesting project where we got to try a lot of the methods we've been learning, and if we had more time, you could always try to tune things a little bit better with, but because of time constraints and limits for our computing power.
We had about like 10 days.
Yeah. So, so it's definitely, we learned that to do well in a Kaggle competition is a very time-consuming process, and while your quick and dirty machine learning model can do very well, if you really want to just do a few percent better, then it takes, that's where a lot of people on Kaggle spend most of their time, just trying different things. And but if you create like a good pipeline for how your workflow is going, then it doesn't become too cumbersome. So I think that and also, so basically this data set, it's a really good way to compare different machine learning algorithms on. And if you see and a lot of the pitfalls that we found, they might show up in other data sets in the real world. So that was probably the main benefits we got from this project. So, any questions?
For doing that, do you try a whole bunch of alphas, or do you sort of pick one or two?
We picked this 3.51 but what we realized is no matter how we change, the accuracy that we pretty much remain below 60%. So it will really improve in that regard.
We also tried choosing our lambda in a few different ways.
I think we mentioned that. So we tried. So what we tried was we looked at we predicted for each lambda, and the one section of lambda that we are interested in, we looked only at the mode of the predicted values. That is the most frequently occurring class value for the prediction for each of the lambdas, and we used that as a final model. It didn't make it worse, but it was definitely like pretty good, and it was still below 60% as I said. So we had to try elements of improve our accuracy.
These accuracy numbers are In sample or outside?
Yeah, so they are out of sample. The out of sample observations are more than 565,000, and we had about 15,000 as income. And we did not really know the class of the 500,000 observations. So we had to post it on the Kaggle website, and that would give us the score back, the accuracy score.
What's the response variable that you predicted?
That we what? Sorry?
What's the response variable that you predicted?
So we're predicting the 7. So whether it was which of these 7 trees were within those 30 by 30 meter spaces for each observation. So whether so it was 1 through 7. So whether it's spruce or pine or aspen.
Okay, and how is it going to be used in practice?
So any forestry people in the house? No.
Because I'm wondering how this regional data were collected. Is it like remote sensing from satellites?
Yeah. It is for remote sensing, also for terrain mapping in forestry. So, and I think those are the 2 main applications.
And there were only 7 classes. So.
You mentioned you were picking the number of trees for the tree-based models. Is overfitting an issue, or basically you just got to pick a time to stop, or is there more to it than just the possibility of overfitting that you just need the time to stop?
Yeah, so I think that is precisely what we are trying to do to avoid overfitting, and we want to ensure that we kind of we just take it out of sample and we vary the number of trees to ensure that we choose the optimal number of trees.
Should you find overfitting actually be an issue with trees? Or, as far as I know, random forest tends to not have overfitting.
Yeah, but I think the number of trees probably does matter to optimize, but it's not the most important parameter to optimize in a business model.
Or I guess we also were looking at number of trees to make sure that to optimize computing power and the speed of running the random forest. So.